Hello and welcome to another session of information retrieval. Today we'll ask the simple question of how do we store a dictionary? Okay, so what is a dictionary? Let me refresh your memories. So we have an inverted index with a dictionary of terms, and each term is pointing to a list which we call as the postings. This contains the document IDs that contain the term at hand. For example, so we have a dictionary here with the terms Brutus, Caesar, Calpurnia, and so on. And also we have a postings which says that the word Brutus appeared in the document ID 1, the document ID 2, document ID 4, and so on. Document ID 5 had Caesar and not Brutus and Calpurnia. So this is how we constructed our inverted index. And the problem at hand today is how do we store this dictionary? One approach is to store them all in a file and go linearly one by one and compare with the query. So if I have an incoming query as Brutus, then I could open this file and check one word at a time and find whether this word is a known word or if this term exists in my dictionary. Um, in this case, the average number of comparisons is of the order of n. Can we do this better? Of course, there is a way to do this better. We could do a binary search if we had ordered all the terms when we wrote them in our dictionary, in our file. Okay, so now we have improved our search for the terms in the dictionary from order of n to an order of log n. Can we do even better? It turns out that there are better techniques for even faster lookup. So we could get a near order of one lookup by hashing. Of course, it depends now on how good our hash function is. Here is a simple example of a hash function where I simply take the ASCII values of each of the characters in the given string and sum them up, and that gives me 52. So for any term that I want to add to my dictionary, I simply sum up all the ASCII values uh, of that string, and with that number I go look up in my hash table, and let's say this is my hash table. The 52nd entry would have hello sitting there. You must have noticed already that it's possible to get multiple strings to return the same hash value, in which case we say we have a collision. One way to resolve the collision over here is to have a list at each of the locations possible, and we keep adding items to the list. So if there is a collision, then we have multiple elements in that list. So the way we would do the search then is, so let's say if I have to find Brutus, I compute its hash value, go to the hash location, and then keep go traversing through the list linearly till I either find Brutus or say that Brutus doesn't exist in my dictionary. So let's take the example of Tony. Tony hashes to 79, let's say. So I come over here and then I follow the pointer from here. I first visit Juliet. Juliet is not whom I need. Catherine, not either. And then I find Tony. So I say the our dictionary has the term Tony. Uh, if I was looking for some other term which doesn't exist in my dictionary, I would have traversed all through this 79, which I assume is the hash value. And then since I don't find the term that was queried, I would say that doesn't exist in my dictionary, and hence I wouldn't return any document. Hope that makes sense, but there are some problems here. We need to come up with a very efficient hash function. Otherwise, we would end up spending lots of free spaces. And in the worst case, it's even possible that only one of this hash table row is filled, and that has all the terms in our dictionary, which would really look ugly. That's not what we want at all. Uh, Another way that people have tried is to use binary search trees. So several such structures have been useful for searching and storing strings. In the binary search tree, we use a search tree in the sense that we have a binary tree at the first place, and uh, for any node. we go to the left if we are looking for something which is lexicographically smaller, and we go to the right if we want something which is lexicographically bigger. So let's say we have m, the character m in the root. Then if my search term is Brutus, so I am looking for a word which starts with B. So let's assume root represents the first character of my term. Obviously I want B, which means it's lesser than M. So I go to the left subtree and I search for Brutus in this left subtree. Again, from this node I look for R. So anything oh sorry, I'm looking for B from here again, and I again go to the left subtree till I reach the term Brutus. So the dictionary terms in this tree are stored in the leaf nodes, and one problem here is that we would like the tree to be balanced. If the tree is not balanced, then we have to do lots and lots of comparisons. So balancing this tree becomes a concern. So can we do even better? That's another question. We could have B trees. Don't confuse these with binary trees. Binary trees are trees with trees where every node has two, at most two children. But in B trees, we have no such restriction. Nodes may have any number of children in the interval, let's say A to B. So here's an example. So we could use B trees to store the terms. So let's say I have the root, and from the root I have, let's say, A to Z as all the child nodes, and within A to Z I have again A to Z as child node. So that way I could traverse the tree in the order of number of characters in the string to locate them. Tries reflect this idea. So here we have again the leaf nodes carrying the keys that we are looking at. So let's say if we are interested in ant, we have the root pointing to A, and A pointing to N pointing to ant. So A, N, and ant. So this way we only need as many comparisons as there are characters in our string to reach to the term that we like. These dictionary representations lead us to easier ways of achieving our queries. So one of the complicated query types that we have seen are wildcard queries. How would we process wildcard queries with a dictionary like this? So let's say I have a query monstar, and the user might have meant Monday or a monk. We want to retrieve all the words in our dictionary which starts with MON. So in other words, um, I want all the words in the range MON to MO and the next character of N, let's say MOO. Um, so, um, and I mean, here is another example, starmon, meaning we want something which ends with MON. And this is even harder. So how would you process these kind of queries if your dictionaries use these kind of data structures? So that's the food for thought here. One way that we could do this is to maintain an additional B tree for the terms going backwards. So that way we can retrieve everything in the range NOM. So just reverse this. Um, Anything between NOM and NON is what we want to retrieve using a reversed B tree. For instance, I have a B tree, but the character I start with is the last character of the search string, in this case N. How can we handle the stars in the middle of the query term? So let's say if I have CO star TION. So we could look up for CO star, we could look for star TION, and we could do an AND between them. This is indeed expensive, but it works. Um, Now, how could you do a do this in a better way? Well, we could use permutum index instead. Um, So in the permutum index, we take the term, append a dollar as an end marker. So hello dollar becomes one of the representations of the term, and we keep rotating this term in all possible ways. So we get all the permutations here. So we have LO dollar H, meaning H has rotated to the end, and then we rotate E to the end, and then L to the end, and so on. So we have all the forms, all the unique forms of hello dollar here. Why are we doing this? Whenever we get a query like this, he star lo, we perform a similar rotation here and do a prefix match. So if we get a, so of course we do also add a dollar to the query term, and then do the location then do the rotation. So obviously, for some rotation I should get let's say lo dollar he, and that should match as a prefix to this term. And whenever there's a prefix match, I pick all the words in my dictionary where I get such a prefix match and return as potential matches. All right, this is interesting, but what if I had multiple wildcards in my query? Something like this, H star, L star, O. Can you think of a way where I could still use a permutum index? Here is a clue for you. You can enumerate all matches for O dollar H star, and then check in those results if they contain L. Yeah. Um, so in order to deal with with these kind of queries, we could revert to k-gram index of wildcard queries. So in a k-gram index, we use k-gram sequences to point to the query terms, to our dictionary terms. For example, 3 grams in India are IND, NDI, and DIA. This is assuming I'm not using any end markings, but if I do use end markings like dollars, then I would get 3 grams like this. Okay, so let's try to now see whether we could match them. So if I have a query like IN star IA, I could match the first and the last trigram. So dollar IN and IA dollar. So that way I would match India, inertia, and so on. So what would be a 3-gram conjunctive query for red? Take a minute, pause, and think for yourself. You should be careful here because if we use an n marker as dollar, and then try to form a 3-gram query, dollar re and red, uh, remember it will not match all the terms with red star. Why is that so? Well, what are we doing here? We are looking for all the words that start with re and also has red in it, but that doesn't mean it starts with red. As an example, consider retired. Yeah, so the word retired does not match red star, but it starts with re, yes, and it also has red. So retired does not match this query. So before you come up with this kind of an answer, you should be really careful. So we need another post filtering step. After we run this query, on the results that we get, we need to check whether the result matches for red star. So at least we have now a lesser number of documents to do a direct check. That's all it is for today. Look forward to see you again. Thank you.